When the U.S. Air Force repaired the A-10's massive 30mm Gatling gun and tested it, they discovered something surprising.
It's 21 feet long. It's the heaviest gun, automatic cannon mounted on aircraft. It weighs more than 4,000 pounds.
The GA-AU-8A Avenger gun didn't just work properly. It worked better than anyone thought possible. The GA system holds 50 rounds. It fires approximately 3,900 rounds a minute, the first second of fire. The engineers watching the test were shocked. The performance data they were seeing shouldn't have been possible. The gun was now performing better than it had in decades of previous records. Something unexpected happened during the repair work. What they found would make them completely rethink what this weapon could do. The beast returns to life inside a reinforced testing hangar at Eglin Air Force Base. Technicians made their final adjustments to the freshly repaired GAU-8A cannon. After months of intensive maintenance work, the moment had arrived to see if the repairs had restored the weapon to its original destructive capability. It's 21 feet long. It's the heaviest gun automatic cannon mounted on aircraft. It weighs more than 4,000 pounds. The 7 barrels gleamed under the fluorescent lights, each one precisely machined and inspected down to microscopic tolerances. What nobody in that hangar knew was that they were about to witness something that would redefine their understanding of this weapon's true potential. The A-10's primary weapon had been through a complete teardown. Every component stripped, cleaned, measured, and either refurbished or replaced. This wasn't routine maintenance. The cannon had logged over 23,000 rounds, pushing it past the standard barrel life expectancy. Engineers had discovered wear patterns that raised questions about how the weapon would perform under sustained fire. Would the repairs hold? Could the system still deliver the accuracy that made the Avenger legendary? The test would answer everything. The preparation alone took weeks of meticulous work. The hydraulic motors that drive the rotating barrels underwent complete rebuilds. Seals, gaskets, and pressure sensors were replaced with components manufactured to tighter tolerances than the originals. The feed system, responsible for moving ammunition from the drum through the gun and returning empty cases, received particular attention. Every roller, every guide rail, every tension spring was examined under magnification, looking for stress fractures or deformation. As the gun powered up for the first time after repairs, hydraulic motors hummed to life. The barrels began their rotation, each one cycling through its firing sequence with mechanical precision. The targeting system locked onto distant impact zones. Every sensor in the facility came alive, ready to capture data that would determine whether this iconic weapon could continue its service or if its best days were behind it. The control room filled with engineers watching multiple displays showing real-time data from pressure sensors, vibration monitors, thermal cameras, and high-speed footage that would capture every millisecond of the firing sequence. Numbers that don't make sense. The initial test firing lasted just a few seconds. In that brief window, the repaired GAU-8A sent 195 rounds downrange at 3,900 rounds per minute. The GAU-8 system holds 50 rounds. It fires approximately 3,900 rounds a minute the first second of fire. When engineers reviewed the impact patterns, something seemed wrong with the data. The groupings were tighter than the weapon's original factory specifications. Not by a small margin, significantly tighter. The team ran diagnostics anyway, certain there had to be an equipment malfunction. There wasn't. The repairs had somehow improved the cannon's performance beyond its designed capabilities. Each projectile, weighing nearly a pound and traveling at over 3,300 feet per second, struck within a radius that defied the expected dispersion pattern. The recoil management system showed perfect synchronization across all 7 barrels. The feed mechanism operated without a single jam or misalignment. Every metric pointed to the same conclusion. This weapon was performing better than when it rolled off the production line decades ago. Engineers immediately began analyzing what had changed. The new barrel sets had been manufactured using modern precision techniques that hadn't existed when the original Avengers were built. Recoil adapters had been tension adjusted to specifications that were tighter than the historical standards. Feed system components had been replaced with parts that held tolerances measured in thousandths of an inch. Each small improvement had combined to create something unexpected, a weapon system that had evolved beyond its original design parameters. But the real shock came when they calculated the effective destructive range. The improved accuracy meant the cannon could deliver lethal force at distances that previous models couldn't reliably achieve. What looked like incremental improvements on paper translated into a massive expansion of the weapon's combat effectiveness. The A-10's primary weapon had just become significantly more dangerous. The engineering challenge nobody talks about. Most people see the GA-AU-8A and think about its size or its firing rate. What they don't see is the engineering nightmare that makes it possible to mount a weapon this powerful on an aircraft. The gun produces 10,000 pounds of recoil force, more thrust than one of the A-10's engines generates. Every time it fires, the entire aircraft experiences forces that would tear apart lesser designs. The repairs had to account for every microfracture, every stress point, every component that had endured years of punishment that no other aircraft weapon system faces. The recoil adapters alone presented a challenge that took weeks to resolve. These components absorb and distribute the massive forces generated during firing, preventing catastrophic structural failures. After 23,000 rounds, the adapters showed significant wear patterns. The metal had compressed in ways that textbooks said shouldn't happen under those specific conditions. Understanding why required bringing in metallurgists who specialized in extreme stress applications. The metallurgical analysis revealed that the repeated shock loading created work hardening in the adapter materials that changed their mechanical properties over time. The steel alloy actually became harder and more brittle in specific zones where stress concentration peaked during each firearm cycle. This explained anomalies in performance data from older weapon systems. The adapters weren't failing, but their changed properties were affecting how energy transferred through the mounting system. The discovery led to the development of new inspection criteria that could detect these material changes before they affected weapon performance. What they discovered changed how the Air Force approaches maintenance on these systems. The original recoil adapters had been over-engineered as a safety margin, but years of real-world use revealed they could be optimized. The replacement adapters used updated material science alloys that could handle the stress while maintaining dimensional stability over longer service lives. When installed and properly tensioned, these new components actually reduced vibration transfer to the aircraft frame. The feed system presented its own set of problems. The mechanism that moves 30mm rounds from the drum magazine through the gun and then returns the empty cases operates under extreme conditions. Propellant gases, heat, vibration, and the sheer speed of the cycling create an environment where components fail in unexpected ways. Maintenance crews found wear in places that shouldn't experience high stress. According to the original engineering models, reality had proven the models incomplete. The drum magazine itself, capable of holding 1,350 rounds in a helical arrangement, showed stress cracks along weld seams that weren't predicted by finite element analysis. The ammunition, each round measuring 11.4 in and weighing over 1.5 pounds, created inertial forces during aircraft maneuvers that exceeded design assumptions. Modern computational analysis revealed load paths through the drum structure that 1970s engineering couldn't model accurately. What the barrel inspection revealed. When technicians inserted the borescope into the first barrel, they expected to find the standard erosion patterns that come from firing depleted uranium projectiles at high velocity. What they found instead raised immediate concerns. The rifling showed asymmetrical wear that suggested the projectiles weren't traveling down the barrel in the predicted manner. The throat, where the round first engages the rifling, showed signs of thermal stress beyond normal parameters. Each of the 7 barrels told a similar story. The plasma and heat generated by firing had created micro-changes in the barrel steel's crystal structure. Over thousands of rounds, these changes accumulated. The barrels were still within safe operating limits, but they showed the weapon system was generating internal forces that exceeded theoretical predictions. The borescope footage revealed erosion patterns concentrated in specific areas of the rifling lands. The raised portions that engaged the projectile's driving bands. High-speed camera analysis from previous test firings showed that the plastic driving bands embedded in each projectile were melting from friction heat faster than predicted, creating an uneven gas seal that allowed propellant gases to erode the rifling asymmetrically. This explained the accuracy degradation that appeared after 15,000 rounds in some barrels, but not others. An awesome target set, that we can go up there and play on. They're constantly changing it around. The variation came from microscopic differences in how individual barrels were machined during original manufacturing. Differences that became significant under extreme operating conditions. New barrels were produced by a manufacturer utilizing updated machining processes. Computer-controlled equipment could hold tolerances that 1970s technology couldn't achieve. The rifling was more consistent, the steel treatment more uniform, the dimensional accuracy measurably better. These improvements seemed minor in isolation, but when 7 precisely matched barrels rotated through a firing cycle at 3,900 rounds per minute, those minor improvements compounded into significant performance gains. Testing the new barrels separately before installation revealed something else. The improved manufacturing consistency meant that barrel redo variation had essentially disappeared. In the original production runs, each barrel was slightly different within acceptable tolerances. Modern barrels were virtually identical. This uniformity translated directly into accuracy improvements because each shot behaved more predictably as the barrels rotated through the firing sequence. Laser measurement of the new barrels showed rifling groove depths that varied by less than 0.2 in across the entire 90.5 in barrel length. The chamber dimensions matched within 0.1 in between all 7 barrels. This level of precision meant that each barrel imparted identical spin rates to projectiles, eliminating one of the variables that caused dispersion in the original weapon systems. When combined with the improved recoil management, the result was a weapon that shot like a precision rifle despite firing merely 4,000 rounds per minute. The propellant problem. Firing the GA-AU-8A creates a cloud of propellant gases that engulf the front of the aircraft. These gases contain unburned powder, carbon particles, and various combustion byproducts, and they flow directly over the wings toward the engine intakes. The original A-10 designers knew this would happen and engineered solutions. But the testing after repairs revealed that the gas composition had changed over the years. Modern ammunition uses different propellant formulations than the rounds the weapon was designed around. The newer propellants burn more efficiently, producing more thrust per grain of powder. This improves projectile velocity and reduces barrel fouling. Both good things, but the different combustion chemistry also creates gases. With altered flow characteristics, during post-repair testing, sensors detected gas patterns that didn't match historical data. The gases were flowing in directions that previous models hadn't predicted, reaching parts of the aircraft that supposedly had adequate protection. Computational fluid dynamics analysis showed that the changed gas composition created vortices along the wing leading edge that drew combustion products into areas near the landing gear wells and forward fuel tanks. The thermal cameras captured hot gas accumulation in pockets that weren't adequately ventilated. Chemical analysis of residue samples found compounds that were more corrosive than those from older propellant formulations. The improved ballistic performance came with maintenance implications that required immediate attention. Engineers realized they were looking at a maintenance issue that wouldn't show up for months or years. New gas patterns would cause corrosion and deposits in locations that current inspection protocols didn't prioritize. The testing facility immediately flagged this for further analysis. What seemed like a minor observation during a routine test firing had uncovered a problem that could affect the entire A-10 fleet. The solution involved updating maintenance schedules and adding inspection points, but it also revealed something about the weapon's capabilities. The more efficient propellants meant the projectiles were hitting targets with more energy than the original performance specifications predicted. The improved efficiency translated directly into greater destructive power at range. The Gu-8A was hitting harder than it was designed to hit. Ballistic gelatin testing, conducted after the initial firing trials, quantified the improvement. Projectiles from the repaired weapon retained 12% more kinetic energy at 4,000 feet compared to rounds fired from weapons using older ammunition. This translated into deeper armor penetration and more catastrophic post-penetration effects inside target vehicles. The combination of improved accuracy and increased terminal energy created a weapon that was measurably more lethal than the system it replaced. Accuracy at distance. Military weapon specifications include accuracy standards measured in Miller radians. The dispersion of projectiles around the aim point. The GAAU-8A was designed to meet specific accuracy requirements at combat ranges. The post-repair testing pushed beyond those ranges to establish the weapon's maximum effective distance. The results forced a recalculation of what maximum effective distance actually meant. At 4,000 feet, well beyond the typical combat engagement distance, the repaired cannon was still grouping shots within a circle that would reliably destroy armored vehicles. The combination of improved barrels, optimized recoil management, and modern ammunition created accuracy that extended the weapon's lethal envelope far beyond original expectations. Technicians ran the test 3 times to confirm the data wasn't an anomaly. Each test produced similar results. This changed the tactical calculus for A-10 operations. Pilots could engage targets from distances that provided greater standoff from ground-based threats. The improved accuracy meant fewer rounds needed to achieve the same destructive effect, extending ammunition capacity in practical terms. What looked like a straightforward maintenance and repair cycle had actually upgraded the weapon system's combat capabilities. The data showed something else that caught everyone's attention. The shot-to-shot consistency remained stable even after sustained firing. Most weapons see accuracy degrade as barrels heat up and components expand from thermal stress. The repaired Gu-8A maintained its groupings through firing sequences that should have caused measurable accuracy drift. The new components weren't just matching original performance. They were providing capabilities that didn't exist before. Extended firing tests that emptied the entire 1,350-round drum magazine showed no degradation in accuracy between. The first burst and the last thermal imaging revealed that the new barrel steel dissipated heat more efficiently, keeping temperature gradients across the 7 barrels more uniform. This prevented the thermal warping that caused accuracy drift in older systems. Engineers calculated that the weapon could sustain combat rate firing 35% longer before requiring a cooling period, a significant tactical advantage during extended engagements. The vibration signature. Every weapon creates vibrations when it fires. The GAAU-8A creates vibrations that can be measured throughout the entire aircraft frame. These vibrations stress rivets, crack welds, and loosen fasteners. Over time, they degrade the structural integrity of the airframe itself. The repairs included replacing components specifically designed to dampen and absorb these vibrations. What the testing revealed was that vibration management had improved dramatically. Accelerometers placed throughout the aircraft during test firing showed reduced vibration amplitude across almost every measurement point. The new recoil adapters and updated mounting hardware were absorbing more energy and transferring less stress to the airframe. This meant reduced maintenance requirements for the aircraft structure itself. Fewer inspections, fewer repairs, longer service life for components that weren't even part of the gun system. But a vibration data revealed something unexpected. The frequency spectrum of the vibrations had shifted. The new components changed how energy propagated through the weapon and into the aircraft. Certain frequencies that had caused known problems were now absent from the measurements. Other frequencies appeared that hadn't been present before. Engineers needed to analyze whether these new vibration patterns created different stress issues that might show up later. The improved vibration characteristics also affected accuracy in ways that weren't immediately obvious. Reduced vibration meant the aircraft remained more stable during firing. The targeting system could maintain a better lock on targets. Pilots reported that the aircraft felt more controllable during gun runs. All of these factors combined to make the weapon system more effective in actual combat conditions, not just on a test range. Understanding the scale, numbers on a page don't convey what it means to fire a weapon that sends nearly 4,000 depleted uranium projectiles downrange every minute. Each round weighs over a pound and hits with enough kinetic energy to punch through modern tank armor. The testing after repairs involved firing thousands of rounds into reinforced target areas designed to simulate battlefield conditions. The results provided a stark visualization of the weapon's destructive capacity. The depleted uranium projectiles, essentially 30mm penetrators wrapped in aluminum bodies, behaved exactly as designed. Upon impact, they punched through the armor plate. The uranium core penetrated while the aluminum jacket disintegrated. The energy transfer created devastating effects inside armored vehicles. Secondary damage from spalling and fragmentation amplified the destruction. Each hit represented a catastrophic kill on enemy armor. The test range also included surplus armored vehicles representing threat systems. The A-10 was designed to counter. A single 2-second burst from the repaired GAU-8A struck a decommissioned infantry fighting vehicle with 43 rounds. High-speed photography captured the sequential impacts as depleted uranium cores punched through the front glacis plate, side armor, and turret ring. The interior of the vehicle was shredded by penetrating rods and secondary fragments. Fire broke out within seconds as hydraulic fluid ignited from the heat of penetration. The vehicle was reduced to scrap in less time than it takes to read this sentence. But the testing also demonstrated something that specifications don't capture: the psychological impact of facing this weapon. The distinctive sound of the GAU-8A firing, often described as a deep, tearing roar, comes from the supersonic crack of projectiles, followed by the sound of the gun itself. Targets receive the impacts before they hear the sound of firing. There's no warning, no chance to take evasive action. The weapon hits before anyone knows it's being fired. The testing included firing scenarios that simulated actual combat conditions, moving targets, various angles of attack, different ammunition loadouts. In every scenario, the repaired weapon system performed at or above specifications. The combination of accuracy, rate of fire, and projectile lethality created a capability that few ground targets could survive. The test confirmed what combat veterans already knew. This weapon system represents one of the most effective anti-armor platforms ever deployed. Moving target engagements proved particularly revealing. The weapon tracked targets traveling at speeds up to 35 miles per hour, maintaining a hit probability that exceeded 80% even when firing from offset angles. The improved accuracy allowed gunners to engage targets with shorter firing windows, thereby reducing their exposure to return fire against stationary targets representing Dugan positions. The weapon demonstrated the ability to systematically destroy multiple targets in a single pass, something that had been theoretically possible but rarely achieved with older configurations. What the testing actually revealed. After weeks of comprehensive testing, engineers compiled data that told a remarkable story. The repairs hadn't just restored the GAU-8A to its original condition. They had created a weapon system that surpassed its original performance across almost every metric. Accuracy improved, reliability increased, vibration management enhanced, effective range extended. The maintenance procedures developed over decades of operational experience combined with modern manufacturing techniques had produced something better than the original design. This raised questions about the entire fleet. If one repaired weapon showed these improvements, would other A-10s see similar gains after their next scheduled maintenance cycle? The Air Force immediately began analyzing whether updated maintenance protocols and modern replacement parts should become standard across all aircraft. The testing data suggested that properly maintained A-10s could remain effective far longer than current retirement schedules predicted. A cost analysis revealed that implementing the updated maintenance procedures across the fleet would require an initial investment in new tooling and training. However, the improved reliability would result in reduced overall maintenance hours per aircraft. The extended barrel life alone would save millions in replacement costs. More significantly, the enhanced combat effectiveness meant each aircraft could accomplish mission objectives that previously would have required multiple sorties or additional aircraft. The force multiplication effect made a compelling case for not just maintaining the A-10, but upgrading the entire fleet to this new standard. The destructive potential revealed by testing exceeded what theoretical models had predicted. The weapon didn't just meet the design parameters, it exceeded them in ways that made it more lethal against modern threats. Armor developments that were intended to reduce the effectiveness of the GAU-8A ultimately failed to withstand the improved accuracy and consistency. The old gun, properly maintained with modern techniques, remained absolutely relevant against current generation targets. After repairs, the U.S. tested the A-10's 30mm Gatling gun and discovered a weapon system that performs better than when it was first built. Tighter accuracy, extended range, improved reliability, and destructive power that exceeds original specifications. Modern maintenance techniques, combined with decades of operational knowledge, created something scarier than anyone predicted. What improvements do you think would make the biggest difference in the A-10's combat effectiveness? Could these same advanced maintenance techniques be applied to other aging weapon systems in the fleet? How do you think adversaries would respond to knowing this weapon is now even more lethal than before? Share your thoughts in the comments below.